All right. So we're back at TryHackMe's Pre-Security Network Fundamentals Packets and Frames Task 2 TCP IP, the Three-Way Handshake. So this is a little backwards, but Transmission Control Protocol, or TCP for short, is another one of these rules used in networking. This protocol is very similar to the OSI model that we've previously discussed in room 3 of this module so far. The TCP IP protocol consists of 4 layers and is arguably just a summarized version of the OSI model, right? So basically it's the same thing, but a little bit different, I guess. So these layers are application, transport, internet, network interface, okay? So very similar to how the OSI model works, information is added to each layer of the TCP model as the piece of data or packet traverses it. As we may recall, this process is known as encapsulation, where the reverse of this process is called decapsulation. So we got a new word here. So one defining feature of TCP is that it is connection-based, which means that TCP must establish a connection between both a client and a device acting as a server before data is sent. Okay. Because of this, TCP guarantees that any data sent will be received on the other end. This process is named the Three-Way Handshake, which is something that's going to be discussed later. A table comparing the advantages and disadvantages of TCP is located below. So we've already seen this, but we'll go over it again. So the advantages of TCP are going to be, it guarantees the integrity of the data. It's capable of synchronizing 2 devices to prevent each other from being flooded with data in the wrong order. All right. And it performs a lot more processes for reliability. All right. But the disadvantages of TCP are it requires a reliable connection between the 2 devices. If one small chunk of data is not received, then the entire chunk of data cannot be used and must be resent. So I think that's like whenever you like load a website and it gets all black and like you got to press reload. I think that's probably what they're talking about here. Like something might not have got sent and so you got to reload the page or something. I don't know. Don't quote me. All right. So a slow connection can bottleneck another device as the connection will be reserved on the other device the whole time. Okay. I've seen this a lot on like my bank websites. Also, TCP is significantly slower than UDP because more work or computing has to be done by the devices using this protocol, right? Okay. TCP packets contain various sections of information known as headers that are added from encapsulation. So we're going to explain this. We're going to look at this in some detail. Hold on. Let's explain some of the crucial headers in the table below. So I'm pretty sure these headers is like metadata. So let's just go through it. We got the headers and then the descriptions. So the first one, source port. When this value is the port opened by the sender to send the TCP packet from. This value is chosen randomly out of ports 0 to 65535 that aren't already in use at the time. All right. We've also got a destination port, and this value is the port number that an application or service is running on the remote host, the one receiving the data. For example, a web server running on port 80, right? Unlike the source port, this value is not chosen at random. Yeah, so all these are going to be assigned in the destination ports. So we got the source IP, which is the IP address of the device that's sending the packet. Destination IP is the IP address of the device that's receiving the packet, basically. Sequence number. When a connection occurs, the first piece of data transmitted is given a random number, all right? And then we're going to go into this in more detail later. We've also got acknowledgement number. And after a piece of data has been given a sequence number, the number for the next piece of data will have the sequence number +1. And that's also going to be explained later. We've got checksum, which is the value that gives TCP integrity. It's a mathematical, it's not math, it's arithmetic. Math is like algebra or calculus. This is definitely adding. And there's no subtracting, no division, no multiplication. It's literally just adding. So it's an arithmetical calculation that's an arithmetical calculation is made where the output is remembered. When the receiving device performs the arithmetical calculation, the data must be corrupt if the output is different from what was sent. Anyway, basically it's just those, like when it said the numbers go in order, it's just adding 1 to each one. And if at the end or in the middle, the numbers don't match up, then something got messed up. All right. That's basically what this is saying. So we've got data, the header where the data, i.e. this header is where the data, i.e. bytes of a file, is being transmitted or stored. Okay. And then we've also got a flag, and this header determines how the packet should be handled by either device during the handshake process. Specific flags will determine specific behaviors, which is what we're going to see below, right? So next, we're going to discuss the three-way handshake. This is the term given for the process used to establish a connection between two devices. The three-way handshake communicates using a few special messages. The table below highlights these, right? So we've got step 1 through 5 messages and also descriptions. So step 1 is going to be a SYN, which is for sync or synchronization or whatever. So the SYN message is the initial packet sent by a client during the handshake. So we would send it from here, right? This packet is from like, Chrome or whatever. This packet is used to initiate a connection and synchronize the two devices together. So this is like Chrome is sending a synchronization message to the TryHackMe server, all right? Then we got step 2, which is SYN-ACK, this packet is sent by the receiving device, so the server is sending it back, TryHackMe sending a SYN-ACK back to us to acknowledge the synchronization attempt from the client, okay? And then we got 3-ACK, the acknowledgement packet used by either the client or server to acknowledge that a series of messages or packets have been successfully transmitted. So we send the sync, they send the sync-ACK, and then we send the ACK back to them saying that we got their synchronization, right? Now we got the data, which is step 4. Once a connection's been established, data such as bytes of a file is sent via the data message, okay? Then we got step 5, FIN, and this package is used to cleanly or properly close the connection after it's been complete. So finish, basically. And then we've got this hashtag RST. I'm pretty sure that's for reset. This packet abruptly ends all communication. This is the last resort and indicates there was some problem during the process. For example, if the service or application is not working correctly or the system has faults such as low resources. And don't quote me on this, but I'm pretty sure when we press reload up here, it like if this was loading up and we press reload, I think that's going to send an RST to them as well. So kind of like that, I guess. Again, don't quote me. I don't know for sure. The diagram below shows a normal three-way handshake process between Alice and Bob. In real life, this would be between two devices. So Alice would be our browser and Bob would be the server. Okay, so Alice is sending the SYN, then Bob, the server, is sending the SYN, the acknowledgement, and the sync for the server, and then Alice is sending the acknowledgement that Alice got the sync. All right. So any data, any data given. What? Okay, any sent data is given a random number sequence and is reconstructed using this number sequence and incremented by 1, all right? Both computers must agree on the same number sequence for the data to be sent in the correct order. This order is agreed upon during 3 steps, right? So we've got a little play going on here. We've got SYN, this is going to be the client, which is Alice. Here's my initial sequence number, the ISN, to synchronize with 0. And 0 right here, that's random. It could be any number between, I guess, the 655-35 number. 0 and the 655-35. I don't know, maybe. We got SYN-ACK. That's the server, which is Bob. Here's my initial sequence number. So they got it's Bob sending the ISN to synchronize with, and it's going to be a random number, which in this case is 5,000. I acknowledge your initial number sequence of 0. Okay, so 0 is from Alice, and Bob gave out 5,000. All right, and so now Alice is saying, I acknowledge your initial sequence number, your ISN of 5,000. Here's some data, and this is going to be ISN plus 1. So this step from Alice is 0, and then this step from Alice is, well, I guess not this one, but the data would be 1. Okay, that's basically what they're saying here. And we got this device, client, sender, initial, the ISN is 0. So 0 plus 1, so now it's 1. And now we're doing the second one, which is going to be 1. So now it's 2. And then the third one is 2. So now it's 3, okay? So we're adding 1 to 0, 1 to 1, and then 1 to 2. And that's basically what I meant by when I said arithmetical, wherever that was up here. Wherever it was. Anyway, so TCP closing a connection, right? So we're going to quickly learn the process behind TCP closing a connection, right? First, TCP will close a connection once a device has determined that the other device has successfully received all the data. Because TCP reserves system resources on a device, it's best practice to close TCP connections as soon as possible. And remember, this is all automatically happening. We don't have to do any of this stuff. This is all just happening in the computer, and we're probably going to need to know this stuff so we can exploit it if we're doing hacking, right? Or red teaming or whatever. To initiate the closure of a TCP connection, the device will send a FIN packet to the other device. Of course, with TCP, the other device will also have to acknowledge this packet as well. So we're going to see this process using Alice and Bob again, right? So Alice is sending the FIN after she did the acknowledgement and sent data and whatever. And then Bob's saying, I acknowledge your FIN. Here's my FIN. And then Alice says, okay, I acknowledge your FIN. And that's the end of that. So in this illustration, we can see that Alice has sent Bob a FIN packet. Because Bob received this, he will let Alice know that he received it and that he also wants to close the connection using FIN. So Alice has heard Bob loud and clear and will let Bob know that she acknowledges this. Hopefully all that stuff made sense. I mean, it's pretty simple once you realize it. And then the other thing, it's all automatic anyway, right? So what's the header in a TCP packet that ensures the integrity of data? Let's go up to the headers. That's not it. Here it is. Checksum integrity right here. So let's put checksum in there. Check the sum. Let's submit it. There we go. So provide the order of a normal three-way handshake with each step separated by a comma, right? So we're talking about this right here with SYN-ACK, and ACK right here. Let's come down here and do that. We'll say SYN, and that's not it. SYN-ACK, and then ACK. All right. Let's submit it. And there we go. Awesome. So now we're on to task 3. Oh, I didn't say my all right. All right. So now we're on to task 3, practical handshake. And see you next time.